Recording. Hi everyone, welcome back. And this is, well, let me pull it up here. This is homework 2, part B. So we're going to be looking at this thing called entropy. And we're going to be deriving the expression for it. I'm just going to go ahead and jump in. We're going to be deriving the expression for entropy. So the example I'm going to use for this is if we take some number of students, we're going to call it n. We'll say we'll take 1,000 students. N equals 1,000. And in this number of students, there are different possible grades you can get. So we'll call that ni. And ni can take on any value ranging from 1 to 10. 3 to 10. So this is the number of students, big N, and little n is the grades, the possible grades that you can get. And if we were going to take this data and we were going to distribute it, it would look something like this. Where we'll make a bin for 1, 2, 3, 4, skip a few, 9, 10. And without knowing what this data actually is, what the grades actually are, we could kind of predict what it would look like. So, for example, maybe it's distributed, do this in red, maybe it's distributed kind of uniformly here, like this, where we have 100 students in here, we have 100, 100, and so on. 100 in every bin. This is one possibility. Another possibility, maybe everyone in the class is really bad. And in that case, maybe everyone got a 1, and we have 1,000 here. Or maybe it might work a little bit easier if I change this up a little bit. Maybe everyone got 1, 2. Well, we'll just say another possibility is that maybe half the class got a 1, half the class got a 2. Again, we don't know what this data is. But what the entropy basically is of this data, which one is more likely to actually occur. And in this case, it would be this red one that's uniformly distributed. It's more likely to occur, it has a higher entropy. Now the way we're actually going to express this entropy is with, we're going to take the number of students, so big N, so 1,000 factorial, over the number of possible students or the number of students in each bin. So for the blue, it would be 500 factorial times 500 factorial. And for this red data set, we have 1,000 factorial. Again, we have the same number of students overall, times, but this time we're going to do 100 factorial 10 times. 100 factorial times 100 factorial times, and we're just going to keep doing that 10 times. This is the expression for entropy of the distribution that we use. So what I want to do is express this in a more general way, and what this looks like is it's just going to be big N, number of students factorial, divided by the product, which looks like this pi, from I equals 1 to, in this case, 10. We'll call it 10. And it's going to be of ni, which is the grade, factorial. So this is the expression for entropy. We'll call this entropy. Yeah, this is the expression. So I guess something to keep in mind here is that when we are actually trying to calculate entropy, 1,000 factorial is a very, very large number. Very large. And I would imagine most calculators probably can't calculate that. So what we're going to use is this cool thing called Stirling's approximation, which says that if we take the natural log of this factorial, n factorial, it's equal to n times the natural log of n minus n. Plus this term here is includes the error. We're just going to ignore it for now. It's just the error term. So this thing is the natural log of n factorial equals n times the natural log of n minus n. Why can I not scroll down? There's gotta be an easier way to do this. Oh well. Okay, so taking a look at this approximation, what we can do is we can actually plug in ni in for this n on the bottom here, and then this n factorial on top for the bit well, we can do it on the top of the fraction and the bottom of the fraction. So what this ends up giving us is, well, we want to take the natural log of this. And when we do this, we're going to have the natural log of n factorial minus natural log of this pi term here. So pi times, well, we have the pi times the natural log of ni factorial. And what I can do is I can just plug in this approximation. So n big N times the natural log of big N minus big N equals, and in the case of doing natural log for a multiplication, this actually turns it into basically addition, so it's just going to be a summation. So this is going to be the summation of ni times the natural log of ni minus ni. And actually something we can do here to simplify this is this n here and this n here. I'll just these two terms are actually the same, because if we take the summation of all the possible grades, that's just going to equal the number, or this is the number of students per grade. So if we just sum all of that up, it's the exact same number as the total number of students. And actually, I don't know. I made a mistake here. This is not an equal sign. This is a subtraction. So gotta make more room. Again, there's gotta be a better way to do this. Oh well. I'm just gonna rewrite this. So we have big N times the natural log of big N, total number of students again, minus the summation of number of students per grade times the natural log of number of students per grade. Now, eventually we're going to try and want to maximize the entropy. So for when we're maximizing the entropy, this big N actually stays as a constant. Um, so we don't really need to regard what we can do to change this big N. So we're just going to ignore it, and then we're left with this expression for entropy being this Ni, number of students per grade, times the natural log of that Ni. So this is what we have for entropy. We're going to go one step further. And here we're going to define the probability of getting a certain grade being equal to the number of students that have that grade divided by the total number of students, which is pretty self-explanatory. And then we're going to rewrite that as number of students per grade equals the probability of getting that grade times the total number of students. So I'm going to substitute that in for this expression. So then we have this times the natural log, that same thing, times n. This is going to be in parentheses. And what we can do, this n is a constant, so we can actually pull this n out of the expression. So what we're left with is negative n times the summation of the probability natural log of pi times n equal to n. And through logarithm rules, we can split this up. So we're going to have negative n, total number of students, the probability, natural log of that probability, plus natural log of the total number of students. And then what we can do is we can actually split up this summation. So what we're going to have is negative n, total number of students again, times the probability, times the natural log of n, minus n, times the summation of the probability, times the natural log of the probability. So when we actually format it like this, we can, we're actually able to remove this term here, because the summation of probabilities is equal to 1. The summation of all probabilities is equal to 1, so we cancel that, and then we're left with this this negative n times the natural log of n, which, if we come up here, this negative n times the natural log of n, we cancel this because we don't care about big N, a term with only big N, because it's going to stay as a constant. So when we're trying to actually maximize the entropy, we don't actually care about this term at all. So then what we're left with is negative n, total number of students, times the probability, times the natural log of the probability. And this is actually going to be our expression for entropy. Entropy. And we want to, in the next video, we're going to want to maximize this, which I guess is the same as if we do the inverse of it, the positive version. If we minimize this, it'll give us the same answer. So maximizing entropy, minimizing the negative entropy. That's what we're going to be doing in the next video. So just to review one last time, We derived the expression for entropy using student grade distribution in terms of the number of possible permutations of n objects with the number of I objects being similar, where I is a distinguishing feature such as grade. We found that this right here is going to be the expression for entropy. So thank you for watching, and I will see you in the next video.